Okay, we start a new topic today. So what we did in the last two topics, or I think the last three, are related to basically programming. Of course, relate to embedded system. The most important point, which is functions and bit manipulation. Now we are going to talk about serial communication. So it's again, we'll go back to hardware and how to use this in the embed or modern microcontroller. So I will explain first what do we mean by serial communication. And this is very important topic and very interesting. Probably you know some serial communication, protocols or standards. USB, for example, is a serial serial communication. There are others which are well known and used a lot in embedded system, for example, SPI or serial peripheral interface, and there is as well the I2C. So those are the two most used in embedded systems. If you go to the market, you will find many devices that they are SPI or I2C. So so you can connect them through SPI port or I2C. Of course, I will explain what we mean by SPI. I2C, I'm not going to cover it, but it's a bit similar to SPI. So it's just the concept of serial communication. This is the main concept that you need to understand. And so first I will talk in general, and then I will show you how to use this on the embed with examples. Right. I think so far, if I switch to do you remember in what we did so far? We have a microcontroller. For example, if I connect a dip switch with four switches, this is how we used it, right? So we used a bus of 4 lines. So each is connected to one line. We call this parallel. So the data goes in parallel to the microcontroller. So there is 1 bit for each line. Imagine that you need to connect to your microcontroller 10 devices, and each device will require 8 pins, digital input or output or whatever. It will require 8 pins, and those will be buses. You won't be able to do that, right? Because we are limited in the number of pins that we have in our microcontroller. And so many devices, if you go to the market, you will find that they support serial communication. What do we mean by serial communication? If we take the example of a dip switch, so you will use only one line, but the data will be sent to the microcontroller serially. So for example, if the first switch here is, let's say, off, on, this is what we will get, 0, 0, 1, 1. This is how this data will be sent to the microcontroller. So it will be sent one after the other. So we'll get 0, then 0, then 1, then 1. So the microcontroller should accept this as a serial data, and then it will put it together. Once it's received it will put it together as one 4-bit data. So when it received it one by one. So we use only one line, and then it will put it together in one variable, which will be 4-bit, and then it can use it. Of course, it will take more time. There will be like delays in getting the data compared to parallel, but because of the high running frequency of the microcontrollers, this is fine. You won't notice this, so you can still have real-time, execution. So this is what we mean by serial communication. So data goes one by one on one line. So if this one is 8-bit, again we will have 8 bits. It goes one by one in one line. Is this clear? This is what we mean. So serial communication, we will use less wires or less pins from our microcontroller. And this is the main advantage of serial communication. Of course, there should be other lines. It's not just the one line. there will be other lines for synchronization. What we mean, I mean, there will be issues. I mean, if let's say that we have a sensor, and this sensor provides data. So I have a sensor that I want to connect to it, and it provides data serially. And this data is 8 bits. So the sensor is, this 8-bit is continuously updating. Let's say is the temperature sensor that accepts or that supports serial communication, and it can send data one by one, and the data is 8-bit data. So the microcontroller, if I connect the microcontroller should know, the microcontroller will start receiving bits one after the other. So it should know what is the first bit, what is the second bit, what is the third bit of the first data, and it should know as well, this is from the first data, and then this is for the next data, those are the 8 bits for the next data, and those are the 8 bits for the other data, and so on. So there is a need for synchronization. So the microcontroller should know the bits and should know the data itself, when it starts, when it stops. And those are the challenges that we face when we work with serial communication. So one solution, and it's a very simple solution, is to send a clock signal alongside the data with one clock pulse per data bit. So basically we have the data, so this line is for data, and we have a model line for clock. So there will be data, there will be clock signal, and of course we can work with the rising edge or we can work with the falling edge. So data will be sent, so if I do this, so this means I'm sending 0. So at this, every clock cycle, we have this data. Here we have this data, so it's 1, and then here is 0, and here is 1. So I'll be sending 0, 1, 0, 1. So each clock cycle, it's one data. If there is no clock, this means there is no data. So the microcontroller is not going to read. So you need to understand the concept. And again, remember that the microcontroller is the device that will require data. So when you write the code, you know when you are going to read from the sensor. So when you start requiring the data, the microcontroller should provide the clock. So it comes from the microcontroller. The microcontroller provides the clock, and once we have the clock, the sensor will start transmitting the data. Once the microcontroller stopped providing the clock, the sensor will not send data. As simple as that. Is this clear? So this is what I was explaining. So I put an example here as well. So assuming that we are working with the rising edge, of course, this can be configured, and you will see later on how we do it. So you can work with falling or with rising, but it doesn't matter. At the end, it doesn't matter. So here, assuming that we are working with the rising edge, this is the data that will go to the microcontroller from the device that is connected to the microcontroller. So it's 1 bit is output by the transmitter every clock cycle. So every clock cycle we have 1 bit. Now, how can, in terms of hardware, how can this happen? Do you see this block diagram here? We have 2 parts. And when we talk about serial communication, we use the word nodes as well. We have the master and the slave. The master is usually the microcontroller. And the slave is any device that can be connected to the microcontroller. So we can connect several slaves to the master. And then the master can require data from the selected slave that it wants. Now, what should we have in each device? So for example, here, do you remember when we talk about the analog input, analog output for microcontroller? If I want to use an analog output, analog out. The microcontroller should have a digital to analog converter, yeah? So this should go so we have a hardware or a component called the DAC that is inside this microcontroller that will allow us to output analog data. Same here, if I need to work with serial communication, I should have a circuitry or a hardware inside my microcontroller that will allow me to do this. So for serial communication data transmission. So, and the same for any device that supports serial communication, device 0, it should have as well this to allow things to be connected. So this is what I put in the notes. So those are the hardware that will be required to perform the communications, for the communication to happen. And what do we basically have in those small blocks? We have a shift register. So this is usually the microcontroller, and this is usually a sensor. The microcontroller is the master, the sensor is the slave. I can have many sensors, right? So many slaves. Now, how does it work if I need to use serial communication? So we have a shift register in each one. We have a clock source in the microcontroller, or the master should have a clock source. And the clock goes to both of them. It's the same clock signal. So do you see here? So we have clock and we have clock here. So it goes to both of them. So once you want the microcontroller to get data from the sensor, the first thing that we'll do, it will start the clock. So we will have clock here, we have clock here. And this is a shift register. So this is a shift register, and we have a clock. I think it's better to explain it here if I will redraw this here. And let's give you an example with, let's say the shift, we will transmit data of 4 bits. So data could be 4-bit, could be 8-bit, could be 16-bit, depending on the sensor. Right, so you find this information in the data sheet of the sensor. Right, and then we say we have clock source. So this clock goes here and it goes here as well. And then we have 2 lines like this. And do you see, this is like a rotation. You can think of this like it's one shift register rotating. For like an 8-bit shift register rotating. But it's actually 2 4-shift registers. And then assuming that I have the data here, this one, 1, 0, 1, 0. So at a given time, the sensor, this is the sensor, right? And this is the microcontroller. So the sensor has this data. And the microcontroller wants to get this data from the sensor. So it will start the clock. Once we have clock here, what will happen? You know, a shift register consists of flip-flops. If you remember, we did this in digital, yeah? So and this clock goes to all flip-flops. So every clock cycle, the data will go out from one to the other. So the data will be shifted. So first, if I put here, first clock cycle, what will happen? What do we have? And assuming here we have 0, 0, 0. Here we start with 0, 0, 0. First clock cycle, what do we have in the sensor shift register and what do we have in the microcontroller shift register?